equipment. This is the beginnings of what we are calling our Smart Structures Laboratory. This is Dr. Craig Rogers here, who will show you one of the things he's currently working with.
In the Smart Materials and Structures Laboratory, we're beginning to investigate new concepts for adaptive materials and structures. New materials and structures that have adaptive capabilities for being able to vary their material properties based upon environment or varying loads, that can control damage in structures. We use a lot of different types of novel materials, such as shape memory alloys. This is a piece of nitinol, and it has unique adaptive capabilities in that once it has been deformed plastically, it can revert back to a memorized shape by simply heating it and going through a phase transformation. We then use these materials in composite structures in order to use the varying properties, adaptive capabilities, for being able to control motion, say of composite structures, to be able to change the material properties in order to stiffen them or to control damage. We're also very interested in large space structures as part of our laboratory effort, and are looking at other sort of novel concepts for being able to control large flexible space structures.
Our student, Harry Robertshaw, he's actually a faculty member, but he likes to disguise himself as a student, as you can see. He'll explain what this beast here is all about. Harry?
Thank you. This is part of our adaptive truss effort, or active truss effort, and the idea that this is a part of a deployable truss that they could send up on the space shuttle, for example, and it would erect itself. Now, one of the problems that they've had with these things is since they're light, they're going to vibrate in space. And so our contribution to this effort of vibration control with an adaptive truss is to make the links change their length. And so you can see on the top there that we have variable length links. And so when this truss will start to vibrate, the links will change length and control that. In addition, this is also what we call a parallel robot, or a variable geometry truss, and we're going to demonstrate part of that activity for you now, where this thing has a rigid pen attached to it, and we'll draw some letters. All right. And so this thing is moving over now, and it's going to draw NASA for NASA, the people that sponsor this work. So it's going down to the paper now and is drawing the first part of the letter N. Now this is a 14-foot long robot. Now it's going to come back and continue with the N. Okay, that's good. We are currently building another one of these things with 21 motors in it to do shape control and other kinds of control for structures in space.
What we have here is a mechanical engineering laboratory class. They're about to run a test on an internal combustion engine with fuel injection to compare its performance with an older model engine that has a carbureted fuel supply. What you're looking at here is our anechoic chamber. It's simply a room designed such that all of the sound that reaches the walls is absorbed. None of it is reflected back. We use this to study the noise characteristics of various types of machinery. By putting the machine in here, we can isolate the sound radiation and pinpoint exactly where it's coming from. These students are working on a new model of a little formula racing car for a contest sponsored by the Society of Automotive Engineers. Later, what you're looking at here is a brand new 4-axis computer-controlled milling machine. This thing will be direct wired to the CAD/CAM laboratory upstairs that I showed you earlier. It's new, it just came in, we're just checking it out. Show you our gas turbine test facility. You can see the sign on the wall here. It says Turbo Machinery and Propulsion Research Laboratory. We'll now move into the test cell. We're now inside our test cell. What you're looking at here is a Pratt & Whitney JT-15D aircraft jet engine. It's a full-size engine that's typically used on a business-type aircraft. The engine belongs to NASA, but it's here on a more or less permanent loan basis. It's been modified for research purposes so we can mount all sorts of gadgets inside the engine and monitor what it's doing. This is a view of some of the instrumentation that's attached to the engine. It may look a little small to you, but don't be fooled. That's a genuine full-size gas turbine engine. This is the exhaust end of it. If you look out the back door of the test cell out here, you'll see some deflection plates. There's quite a blast of air that comes out of this thing, and without that blast deflector back there, it tears up the bank behind the building. It's a rather unique facility. I don't know of any other university in the country that has this kind of capability of a full-size gas turbine engine that we can run whenever we want to here in our own test cell. Next, I'd like to show you a couple of design projects which are a lot of fun. The first one is called a Mini Baja competition. Briggs & Stratton furnishes engines, and the students design and build an off-road vehicle. In the spring of each year, competitive events are held at several locations around the country. What you're about to see first is a rerun of a local television news broadcast that shows our car, and then some scenes from the competition which was held in Montreal last spring.
Virginia Tech Duck Pond hosted a new species of amphibian today. A group of tech engineering students put a year of hard work to the test today as an experimental amphibious all-terrain vehicle took the plunge. The 8-horsepower vehicle took to the water almost as well as its feathered cousins. Part of the ATV's success was attributed to its computer-aided design. Students hope its high-tech advantage will give it an edge on the racetrack.
We're going to Montreal. It's the Society of Automotive Engineers East competition. There'll be about 30 other schools there from all over the East Coast, and we'll be competing against them. From the student standpoint, this is a very real design contest. They have to design the vehicle, and you can see a lot of originality in the design. They've designed the vehicle, had to build the vehicle. They had to build it within cost restrictions and weight limitations, and so it's a real problem.
The vehicle will be judged on its design, power, safety, and its performance in a 3-hour endurance race. One goal of the competition is to find a design that could be marketed commercially.
Another vehicle that our students designed and built is a Formula race car for a competition sponsored by the Society of Automotive Engineers. This little car is not a toy. It's powered by a 4-cylinder Kawasaki motorcycle engine and is capable of reaching 90 miles an hour in a straightaway. We were labeled the junkyard dogs because we had the heaviest, ugliest car made largely from used auto parts. However, the competition soon changed their view when we blew them away in the maneuverability test. What they didn't realize is our car has a tunable suspension. Next spring, we intend to go back and win. If you would like to know more about mechanical engineering, stop by and visit us anytime. Good luck in your freshman courses, and we hope to see many of you next year.